This is an example problem for Physics 1000 at Auburn University, summer of 2013. The second problem we solved in class today was stated as a given mass hangs without moving from a string. And you were asked to find the force in the string. And I mentioned that we will, in a few weeks, we'll begin calling the forces in a string a tension force. So we'll go ahead and call it a tension. But as we said in other examples and in class, the first thing you need to do in these problems is draw a nice clear picture. So what we have is a mass that's hanging, and we have a string from which the mass is hanging. Let me draw that a little more clearly. There we go. So, the first thing to notice about the problem is that there has to be a force in the string. Remember our two-finger rule for determining forces on an object. First finger, gravity. Well, I'm on the wrong tool. Gravity. And the second one is whatever is touching the mass. I guess we'll begin with number 2 here. What's touching the mass is a string. So we know for sure, we are guaranteed that there's a force in that string. And you can probably convince yourself from experience that the force is directed like this. We'll call this, actually we'll go ahead and call this the tension. I think in class I called it an F sub 1. We'll call it the tension here. That's fine. I think you guys can handle that terminology. And so we know also that we can't stop here. And the clue is given in the problem where it said that the mass hangs without moving. Now we know, if you think back to Newton's second law, the sum of the forces equals mass times acceleration. If the sum of the forces, if this term right here is not 0, if that does not equal 0, then you are guaranteed to have an acceleration. Guaranteed. But this mass is not moving. We know that from the statement of the problem. So we know that there has to be another force acting here. And that force is revealed by looking at our number 1 here, gravity. Everything has weight. At least everything in the problems we're going to be dealing with has weight. So it also probably is not too hard to convince yourself that that force has to be going down. So I'm going to call that, not the weight, but as we said in class, we define weight as m and g, m times g, where g is the acceleration due to gravity. We define that in class. And so I'm going to call it mg. And what we're being asked to find is the tension. And I should also note there's a mass here, which we know. So let me make myself some room. Get rid of these guys. And we can start solving this problem. Just like always, I'm going to make a legend. I'm going to tell you what I know. You can also call this givens if you want to. I'm going to tell you what I don't know, and I'm going to tell you the equation that I'm going to use to solve it. So what I know in this case is, let's say m equals 10 kilograms. And I know g. I always know g. G, we've said, is 9.81 meters per second squared. We always know g. So anytime g is in there, it goes in the known column. And so my unknown is t. I don't know what t is. I'm looking for it, so we can say this. And the equation I'm going to use, again, we have mass, we have forces, we have the acceleration, because remember g is an acceleration. Newton's second law is the obvious choice. Sum of the forces equals mass times acceleration, not n. Let me write that a little cleaner. Mass times acceleration. Okay, so let's start to unpack my sum of the forces. I'll come down here to do it. So I'll sort of box off my drawing here. Sum of the forces equals mass times acceleration. My stylus is not doing too well today. First thing I'm going to do is unpack the sum of the forces. And again, like the last example problem, we need to pick a direction. Normally what we see in math is that up is the positive direction and down is the negative. Again, this is completely arbitrary. It's totally up to you. But I'll use this convention with this problem. I'll say that up is positive. So my tension force is in the direction of my positive sign, so it's going to have a positive sign. And mg, my weight, is going down, so it's going to have a negative sign. So when I unpack the sum of the forces, what I come up with is positive t and a negative mg. T minus mg equals mass times the acceleration. Now here is where being really familiar with what the problem is asking is going to make some of these problems a lot easier. Because what's the acceleration in this problem? Hopefully you see that it's 0. If the mass is hanging, it's not moving, then the acceleration has to be 0. So we have the special case we talked about last class period of equilibrium, is when the sum of the forces is 0. And in this case the acceleration is 0. So we have this right here, because if A is equal to 0, then certainly anything, any mass, doesn't matter if it's 10 kilograms, 100 kilograms, a billion kilograms, any mass times 0 is just 0. So what I come up with is T minus mg is 0. Nice. We love when problems are in equilibrium because it makes them really easy. And in that case, I can come right over here and take the minus mg to the other side by adding mg to both sides, and I get T is equal to mg. Remember, T is what I'm looking for. I know m, I know g, so I've got the problem solved. So here is where I put in numbers. It's going to be 10 kilograms times 9.81 meters per second squared. And so the math is easy on this one. You're going to come up with a tension of 98.1 newtons. And notice I went ahead and made the jump for, let me get a different color, a kilogram times a meters per second squared is, well, I said a newton and then I wrote an m. Sorry if that confused anybody. I made the jump that a kilogram times a meter per second squared is a newton. I don't mind if you make that jump here. I assume that you know that. If you have questions about that, please come and talk to me. So that's how you solve that problem. More examples to follow.